My name is Azeem. I'm the Chief Engineer at Atmospheric and Space Technology Research Associate in Boulder, Colorado. The company specializes in space weather products and services, and we work for, provide services to the government and to other agencies like NASA and NSF. The overall objective of this experiment is to see if we deposit large quantities of water in the upper mesosphere, about 50 miles above the surface of Earth, how it impacts the local atmosphere, how it impacts the temperature of the upper atmosphere, how it impacts the dynamics, how things are moving in the upper atmosphere by the sheer presence of the large quantities of water. The Super Soaker team consists of myself and then faculty members from University of Alaska Fairbanks, from Clemson University, and from Utah State University. And the teams from these universities, University of Alaska, Clemson, and Utah State all have graduate students involved in this project, and we certainly appreciate their dedication and their hard work on this project.
My name is Patty Lynn McLaughlin. I'm a master's student at Utah State University in Logan, Utah, working in the Center for Atmospheric and Space Sciences. I'm here in Fairbanks, Alaska, working with my advisor on the Super Soaker mission, and I'm really excited to be here.
What we're trying to study is, can space traffic or increase in space traffic can contribute to the increased observation of these noctilucent clouds. Historically, noctilucent cloud has been studied, and people have looked at their frequency as a sign of or indication for climate change. But if the source is also increased space traffic, an increase in space traffic will lead to more and more noctilucent cloud. And that's what we're trying to assess. Okay, can we create noctilucent clouds artificially? And that will provide us the missing link between increased noctilucent cloud and increased space traffic.
A polar mesospheric cloud, or a noctilucent cloud, is when there are ice particles in the air around the mesosphere region, and the sun hits them at just the right angle, and they appear to be glowing. And so there's two names for them, because originally, when we viewed them from the ground, they were called noctilucent clouds, right? And then satellites would observe them from up high, and they would call them polar mesospheric clouds. And we didn't know that they were the same thing until, I don't know when. Sometime a scientist figured out it was the same thing. And so that's why there's like two names for them.
We want to deposit water at about 85 kilometers, which is about 55 miles above the surface. Rockets provide us a convenient way to deposit water at that altitude. Satellites are too high, and sounding rockets provide us, a perfect tool to sounding rockets provide us a convenient tool for deposit water where we exactly want us to put water in. So we have 3 rocket launches, and we are targeting to launch the rockets during the morning twilight. So the first 2 rockets will carry the TMA payload, and then the final 3rd rocket will carry the water canister, which we will explode when the rocket reaches 85 kilometers, 50 miles above the surface. So the first rocket we plan on launching around 7:30 in the morning. The second rocket with the TMA payload we will launch around 8 o'clock, and 90 seconds later we will launch the 3rd and final rocket with the water payload. So TMA stands for trimethyl aluminum. It's a chemical that ignites when it's exposed to oxygen. So and it's completely benign, so there are no health hazards if you're afraid about that. So we will release this TMA, or start releasing TMA, around 75 kilometers above the surface, and then we'll continue to release TMA up to 150 kilometers. So when it's exposed to oxygen in the atmosphere, it will sort of start to burn or glow. And then we'll use ground instruments or ground cameras to track how this TMA trail is being moved by the wind in the upper atmosphere. And by utilizing multiple camera sites, one can deduce how fast these winds are in the upper atmosphere are moving and what direction they're moving. We are utilizing a NASA-provided aircraft, and that aircraft will carry a camera to track the TMA, trimethyl aluminum trails. So we'll have a camera site here set up at Poker Flat, and then we'll have another site at Coalfoot, and another set of cameras will be flying on the NASA aircraft. And the reason why we're using the NASA aircraft is because we need 2 camera sites. So if the weather conditions in Coalfoot is not favorable for viewing, we at least will have a NASA aircraft with cameras, and that will allow us to use cameras on the aircraft and at Poker Flat to track the TMA trails and get our science results that we want.
During launch, I will be operating a camera here at UAF in the LV building, well, actually on top of the LV building. And the camera is an intensified infrared camera, and we're just hoping to see the noctilucent cloud form with this camera. It's just another source of data.
So there are multiple ground instruments that we're utilizing to complete this scientific study. So in addition to the 3 rockets that we're launching, we'll have a LiDAR provided or operated by Professor Richard Collins from University of Alaska Fairbanks. And then we'll have advanced mesospheric temperature mapper operated by Professor Michael Taylor from Utah State University. And then we'll have a set of other cameras operated by Professor Miguel Larson from Clemson University to track the TMA trails. In addition to these instruments, we'll also have some other cameras, just high sensitivity cameras that operate in the visible in the visible spectrum, and they will be operated by Utah State University. So there are some set of conditions we needed for our mission. That is clear sky conditions, because we're using multiple optical instruments on the ground, and we would like to have clear sky conditions so we can look at the upper atmosphere. This is the first time anybody has tried to create a noctilucent cloud artificially. And if everything goes according to plan, and if we create a large, dense cloud of water, one expect to see these noctilucent clouds by naked eye. But we don't know until we actually do the experiment, because this is the first time we are doing this experiment.
By participating in this experiment, I'm getting a firsthand account of how questions are approached. So you don't really, you read a scientific paper about an experiment that happened, and you see the results and you see what the experiment did, but you don't get to see the process about how people thought about answering the question that they're asking, right? And there's science is so amazing, because like this sounds a little bit ridiculous, right? That the US government is funding a rocket to explode a bunch of water into the air. Like on the surface, it sounds kind of like a waste of money, right? But it's not. And deep down, there's a lot of cool science questions that are being asked, and it'll tell us about the dynamics in that region of the atmosphere. And it is really important work. But these really complex questions can sometimes be answered by a somewhat simple experiment. And I think it's cool to see how those are designed and how it's pulled off. Like this is amazing. There are like 20 people here from NASA to make sure this project goes off smoothly, and the scope of planning and design is just unfathomable. It takes so many people to do this kind of experiment, and everyone is so excited to be here. Like they're all working towards a goal, and it's cool to be a part of that.
This is my first sounding rocket experiment. I'm super excited. It's just going through the entire mission, just from coming up with the concept for a mission and seeing it through, and then being able to see it launch. It's certainly very thrilling. It's a little nerve-wracking, but it's also really thrilling, and being involved in this mission it's a great opportunity, and it's a learning experience from multiple aspects.
personally, I think this research is important because noctilucent clouds, or polar mesospheric clouds, are sometimes thought of as a canary in a mine for climate change. Right, they're very sensitive to changes in temperature of like 2 to 3 degrees, and they can kind of be a warning sign that climate change is happening. And they also affect radio communications. So if, I don't know, the military is trying to communicate and their radio is trying to bounce off the atmosphere and there's a polar mesospheric cloud there, it could not go through, and that messes with communications. So that's kind of important.
Naturally occurring noctilucent cloud or polar mesospheric clouds occur during the summertime. And the reason why we're choosing to do this experiment in the wintertime is so that we can say for certainty that the noctilucent clouds that we're seeing is being generated or created by the water that we are depositing, and it's not being driven by the naturally occurring water in the upper atmosphere. Our success, or our minimum success criteria, is that we are able to release water in the upper atmosphere and able to see the impact of that water release on the temperature of the upper atmosphere. So if we can see the signature in some of the infrared and infrared cameras and the LiDAR measurement, we will consider that our mission was successful and we are going to be able to provide some new scientific insights into noctilucent cloud creation.
So polar mesospheric cloud can sometimes look like, in Harry Potter when he's learning to make a Patronus, and his little wand is just like little wisps of like this airy, bright smoke. That's what it's going to kind of look like in the sky. It's going to be like wispy and thin and glowing. So keep an eye out.